Thanks very much for the invitation. Sorry I'm not here the whole day. I was teaching in the morning and had office hours, so I drove up as soon as I could. And so this is only the second time I have a chance to visit Riverside. The first time was just a few weeks ago for the Southern California BSM meeting, so it's really nice to be back, and hopefully I have a chance to visit many more times. So as Janu said, I'll talk about the early universe, and this will mostly be some big picture overview, but if anyone wants to know more about any of the details in the talk, obviously you can just ask me about them. And I thought I would start with a slide that all of you have seen. Many of you are maybe tired of this slide. I think I wanted to show it because I think it really nicely summarizes what our understanding of the early universe is. So on the very left, if you look at it, it's fuzzy, just like our understanding of the very early universe. And then we know that one way or another, we ended up in a universe that was filled with a very hot and dense plasma. The energy in that plasma caused the universe to expand. The expansion of the universe caused the plasma to cool. As that process goes on, more and more of the degrees of freedom in that plasma freeze out, so the energy or the temperature drops below their mass. They disappear from thermal equilibrium. Eventually, the universe becomes cold enough for atoms to form, hydrogen to form, and that's shown here. So at that point, the photons that mediate the interactions in the plasma no longer have anyone to interact with, and they just free stream through the dark ages. So dark ages in the beginning is maybe a little bit of a misnomer in the sense that at the time the universe was about 3000 Kelvin, which is bright orange in principle, so there isn't initially anything dark about it. But obviously as it expands, it rapidly redshifts out of the visible range, and the universe truly does become dark until the first stars form. Once the first stars form, also the universe gets reionized again to some, and you see from this image that once we're detecting these, anyway, so some of the CMB photons rescatter. This is what is referred to as the optical depth, this contribution. So we have the stars form, galaxies form, and eventually we form. So all of this is something that you can see in the little image. You can also see that just like the scattering I already mentioned, the CMB photons, they might get deflected along their way from the galaxies that you see in this picture. The effect isn't very large, so on average, a photon gets deflected by about 3 arc minutes, but the effect is actually coherent on degree scales, and this is something that you can detect with the CMB experiments. This has been detected, for example, recently by Planck at about 50 sigma. So it's a high significance detection of this effect of weak gravitational lensing of the cosmic microwave background as the photons travel through the matter along the line of sight. And you can also imagine that some of the CMB photons on their way from the last scattering surface to us might get scattered off hot electrons in the clusters. The energy is upscattered, and so they look like a shadow in the CMB experiments. This is what's known as the thermal Sunyaev-Seldovich effect. So in principle, you can see the various contributions that we'll hear a little bit more about the talk in that slide. So for that reason, I like that slide, and I wanted to show it, even though most of you, probably all of you, have seen it many times. So throughout the talk, I'll assume that gravity is described by Einstein's general relativity. If you haven't taken a class on it, you don't really have to worry about it. I won't use any of the more sophisticated things that you might learn in a course on general relativity. I'm only going to really rely on the most basic ideas behind general relativity, which are just that gravitational attraction you shouldn't think of as a force, but as something that arises because space-time is curved. This is what I've been trying to illustrate in this thing here. So the idea is that it's not so much that there is a force between the Earth and the Sun, but the Earth moves on its orbit just according to the local curvature of space-time it sees. And similarly, the geometry of space-time is determined by the matter distribution. So both the Sun curves space-time around it, the Earth curved space-time around it, and they both move in this curved space-time. Now, to describe the geometry of space-time, we use the line, what's known as the line element, which I'm showing here. It's just a way to encode how far apart from each other points are that are close to each other. So if you look at, and we're lucky enough in a sense that the spatial geometry of our universe is very simple. It's just that of Euclidean three-dimensional space. Didn't really have to be that way, but experimentally it turns out that the spatial geometry is just Euclidean three-dimensional space. And so here, as various points, I'm showing you a bunch of galaxies. And what we typically do is we work in co-moving coordinates, meaning that we assign some coordinate to this galaxy. Let's say we call this one 0, 0, but you see it's translational invariant, so you could put any number there, but we call this one 0, 0, let's say, then this one is 0, 1, 1, 0, 1, 1, and then the distance between these two galaxies in those units is just 1, and we have to keep track of the physical distance by including a scale factor into the line element, and then obviously this distance here is just square root of 2 times the same scale factor and so on. So this is how you might think about the line element for this simple picture. As the universe expands, the galaxies move away from each other, and the distance, the co-moving distance between these two galaxies is still 1, but the scale factor has changed, so the physical distance has changed. And you can put that together into a little movie where you have the geometry as of the evolution of these galaxies as a function of time just flying away from each other. And this is what this line element encodes. And you see that the geometry of space-time for our purposes is just described by the scale factor a of t. So you just have to keep track of one function of time to keep track of what the universe is doing, at least what it's doing on average. You can see from the previous slides that changing the overall, the scale factor overall is just a change of units, so the physical quantities can't depend on it, at least not in the geometry that I just described, the flat Euclidean space, and the physical quantities have to be independent of the normalization of the scale factor. So the quantities that are interesting to study are ratios of the scale factor at different times. So you might be interested in the value of the scale factor at some time t divided by the scale factor at the present. This one is often set to 1, but that's again just a choice. So you can call the overall scale factor what you like. And this ratio is typically called 1 over 1 plus z, where the z here is the redshift. And the reason it's called the redshift is that you can ask, if you have a source that's emitting light at some early time and we see it today, what is the wavelength of that radiation with which we're observing it today? And it turns out that the observed redshift is the observed wavelength is the wavelength of the source times 1 plus z, where z is the redshift. So if z is equal to 0, in other words, it's emitted right here, the wavelengths are the same. If it's emitted very early, then the wavelengths are dramatically different. So it's just the radiation redshifts stretches as the universe expands. Another quantity that's interesting that is independent of the normalization of the scale factor is the fractional rate of change of the scale factor, and this is called the Hubble rate. So it's giving you an idea what the expansion rate is of the universe. And now this is the one equation from general relativity I'm using, but it's very simple. The slogan that I had earlier, that the matter tells the geometry how to curve, in this case just tells you that the energy density in the matter, radiation, and in here dark energy tells you what the Hubble rate is. So you see that h squared is proportional to the energy density, and the statement that the geometry tells the matter how to move just tells you that the energy density of the matter scales like 1 over the scale factor cubed. This is relatively easy to understand physically. It just means as if you have some So this is just non-relativistic matter, just a bunch of masses distributed through space. And then if you make the box bigger by a factor of 2, but you keep the particles the same, then obviously the energy in that box stayed the same. The volume went up by a factor of 8, so the energy density went down by a factor of 2 cubed. So it's just the expansion here that you're seeing. It's just 1 over the volume that you're seeing here. For radiation, it's different because the wavelength as the universe expands also stretches, and so you get an additional factor of 1 over A, so the energy density in radiation redshifts like 1 over 8 to the 4th. And then for dark energy, we don't really quite know yet, but the assumption, the typical assumption, is that it would be like a cosmological constant, so it doesn't change at all as the universe expands. It's just constant. The question is, if you look at the night sky, you might have asked, I mean, how can you actually measure these kind of things? All we see are some little bright dots in the sky, so how would you actually go about measuring it? And life would be very easy if we could just take some standard candles, so some object for which we know exactly how much light it emits, and we place them all over the universe, and we measure what the flux is that we see from the various objects that we put there, because that gives us a way, using energy conservation, just to define a distance to that object, and that distance in an expanding universe would depend on the composition of the universe, how much matter there is, how much energy density there is in the cosmological constant, just because the universe is expanding. So you have, if with the standard candles, you could map out the luminosity. This is called the luminosity distance, so you could measure the luminosity distance. Similarly, if you had little standard rulers that you can spread out over the universe, you could look at the ruler, and let's say it's transverse to the line of sight, so it's transverse like this. Then I can define a distance that's defined by the size, the physical size of the ruler divided by the angle it subtends in the sky. So here I'm obviously assuming that the angle is very small, but so this will be the case for the kind of rulers I'm thinking about. But so you could define what is called an angular diameter distance. Similarly, if you take these rulers and they're aligned with the line of sight, you can convince yourself that you can see that the universe is expanding, the expansion rate of the universe from looking at the ruler. The problem is that we can't go out and sprinkle them throughout the universe, but nature left some standard candles and standard rulers there for us. The standard candles are the supernovae, and again the question is, how would you actually use this as a standard candle? Because a generic supernova, you don't really know how much energy was released, how much light it emitted. So there's a special class of supernovae that you can use. They're called the type 1a supernovae. Now you might ask, well, all I'm seeing is a little bright dot. So how do I know what type of supernova it is? And the way you would do that is by looking at the spectrum. So this is the characteristic spectrum. From these lines, you can tell what's actually blowing up. The special thing is that you have no light elements, no hydrogen lines, but you have silicon lines and so on for the type 1a supernovae. So if you look at other spectra of type 1a supernovae, they're really quite characteristic. You see the same pattern, so you can tell what's a type 1a supernova. The type 1a supernova, the idea is that it's probably coming from some binary system where one of the stars is a white dwarf, and it accretes matter from its companion. It flows onto the white dwarf, eventually pushes that over the Chandrasekhar limit, and it explodes. And because it's related to the Chandrasekhar limit, the idea is that the light or the amount of energy released is roughly the same in these. It's not really quite the same, but it turns out that you can calibrate fairly well empirically how much is released by looking at the light curves, how long the supernova actually takes. So these are maybe not quite standard candles, but at least candles that you can calibrate. And so you can use these to do these cosmological measurements. And you can use them in two ways. one of the ways that has been used, that is well known, is to measure the expansion rate of the universe today. So what you do is you measure the luminosity of type 1a supernovae. So in this case, in the measurement from last year, from 19 nearby supernovae, and you want to make sure that you have, in addition to that, a way to really know what their distance is. This is typically done with Cepheids. Once you've measured these, you measure the Hubble rate. Once you've calibrated them, you measure, this is somewhat crude, but roughly you then measure the Hubble rate by measuring the redshift and the flux. So these are things that you can measure. This is the quantity that you have to figure out. This is the quantity that you can figure out roughly with help of the Cepheids and the local supernovae. And then for this quantity, you can just measure it for many more supernovae. You don't have to have Cepheids in the same host. So you can use 300 in this paper, and you get a measurement of the expansion rate of the universe of around 73 kilometers per second per megaparsec. There's some discussion of a tension between this number and the number that's inferred from the cosmic microwave background. I won't say much about it, but if anyone is interested, I'm happy to discuss it more. The other way you can use it is not really looking at the normalization, but just looking at the shape of what we defined earlier, the luminosity distance. So the Hubble parameter drops out, but from the shape, you can still extract the information about the composition of the universe. So you can use it to infer how much matter there is, how much dark energy there is, and then you get these plots from this joint light curve analysis. And this is the measurement that's telling you that there's some non-zero component of dark energy. So that's one of the crucial measurements that tells us part of the story of our universe. Another set of measurements that I also won't say much about in great detail, I'll spend most of my time on the cosmic microwave background, but another set of measurements that's very important for our understanding of the early universe is coming from large-scale structure surveys, and here the one I'm highlighting are the baryon acoustic oscillations. And here what you're looking at here is the correlation function of galaxies. And the way to interpret this is one way to interpret it is as a conditional probability. Given that a galaxy is at 0, what's the probability for finding another galaxy some distance away from that galaxy? And you see that it's a smooth function all the way until here, but then there's some bump, and then it becomes a smooth function again. And so this is telling you that there's some distance at which you're more likely to find other galaxies. So if you take a galaxy and ask what's the probability for finding another galaxy some distance away from it, you're most likely to find one, or more likely to find one in this range than in other ranges. And so the question is how that comes about. And the physical picture is relatively simple. I won't go into details, but I can, I think, give you a basic idea. So we said that the early universe is filled with a very hot and dense plasma made of electrons, protons, photons. There's some neutrinos around, some trace elements, and so on. I haven't yet explained, and I will only briefly mention later, but the initial conditions are such that if you have an overdensity in the matter, then at the same place you also have an overdensity in the baryons and the neutrinos and so on. These are called adiabatic initial conditions. And for such an initial condition, or in general, it's maybe not surprising to think that you might see galaxies later on in the universe in places where you had initial overdensities. Those collapse and you see structures form there. So it's interesting to think about what happens to an initial overdensity in this baryon photon plasma. And what happens is that you have some sound wave of the material that's propagating outward with time. As this sound wave from the initial overdensity is propagating outward, the universe is expanding. As it's expanding, it's cooling, and eventually the photons and baryons decouple. The photons keep free streaming, but the baryons, the speed of sound of the baryons goes to 0, and you've created some shell of baryonic material around this initial overdensity. And obviously through gravitational attractions, then some of the dark matter will get pulled in, and similarly at the location of the initial overdensity, some of the baryons get pulled back in, and so you have an initial spike with a little ring around it, and this is the kind of ring that you're seeing. So you're seeing these spheres around the initial galaxy where you're more likely to find another galaxy. So that's the basic idea, that you have this outgoing shell of material that eventually stalls. And that also, this prescription also tells you how big that should be. The size should be given by the co-moving sound horizon at decoupling. And that allows you, it's related, as we saw, the physical and co-moving distances are related by the scale factor. So if you measure the physical distance and you know what the co-moving distance was, you can actually map out the expansion history of the universe. So this is how it's used, and this is roughly what's shown here. So I didn't properly define what these quantities are. I can define them if anyone really wants to know. But the basic upshot is that these are the measurements from the baryon acoustic oscillation surveys. This is BOSS-CMASS. This just labels what type of galaxy you're looking at. And then this is actually not a fit to the data points, but this is the prediction based on the Planck data. So in this sense, the idea is that the data is very consistent with our basic model of the early universe. And there's a lot of work, as many of you I'm sure know, on looking for these with the dark energy survey, LSST, Euclid, WFIRST, HETEX. So there's a lot of activity in this field, and I can't really do it justice. I only have 2 slides. And I'll move on and go back to higher redshifts now and talk about the cosmic microwave background. And I think here I just wanted to give you an idea of the experiments that happened. Many of them I'm sure you've seen. So there was COBE, WMAP, Planck, the big satellite missions. But then there's also smaller experiments that are important just to move the field forward. There's ABS, Atacama B-mode surge, ACPOL, also in the Atacama Desert, with the Atacama. The other experiment that Jan already mentioned is located at the South Pole, is the BICEP-Keck array series of experiments, and you can see the SPT pole experiment over here. There's Polar Bear, which despite its name is in the Atacama Desert, so you can maybe guess that it wasn't always supposed to go here, but it's in the Atacama Desert. And then there's Spider, another balloon experiment. So there's a lot of activity on the experimental side. I wanted to briefly give you some perspective of how this started, and I'm not going into details really of the history of CMB measurements. I'm just, because I think much of the history is probably known. It's the story of these 2 collaborations. I think it's relatively well known, so I don't want to go through it in detail. If you haven't heard about it, you can ask me or read any of the books that have it. I can give you references if you're interested. So here, this was a measurement from 1965 that first detected the radiation. This is this paper by Penzias and Wilson, and around the same time, Dickey, Peebles, Roll, and Wilkinson gave the interpretation of this measurement in terms of cosmic black body radiation. They were also working on their own experiment. And obviously, as soon as you say that this is cosmic black body radiation, there are a lot of things to be confirmed, because this is a measurement at a single frequency, so you can't really conclude that this is black body radiation. Could be a lot of other things. So the first, so it's obvious that you might try to then measure the spectrum to confirm that it is black body radiation. And here I'm showing you the measurement from COBE, from the FIRAS instrument on COBE that's very well known, where you have a beautiful measurement, our best measurement of a black body spectrum. And the one thing I wanted to highlight is that another group of scientists actually were working on the same thing. Both groups were working on it for a very long time. I mean, it's not that this was quick. I mean, this went on for, the preparations went on for something like 16 years, and this measurement has largely been forgotten. I just wanted to show it because I think it deserves maybe a little bit more credit than it usually receives. So this was an experiment by Herb Gosch, Mark Halpern, and Ed Wishnow, who measured the black body spectrum with a sounding rocket. Also had a very nice measurement, but were just a little bit late. So I think if this had come out earlier, you would all know about it. They were a little bit late, but both groups were working on it for 16 or so years. So these are both remarkable experiments that measured the black body spectrum. The other prediction that you have is once it's a black body, you know there's some preferred frame, which is the rest frame of the plasma, and it's unlikely that we're in that frame. It's likely that we're moving with respect to it. So there should be some dipole radiation that you're seeing. And this dipole radiation, people were also looking for early on. So there were measurements by Conklin and then by Paul Henry, who was the first to measure declination, right ascension, and the magnitude. And this measurement really is still consistent with what we know today, except the precision is much higher, as you can tell. The reason I'm showing this one is I like it because you can see it's done by a single person. So he did all the aspects. He built the experiment, launched the balloon, collected the data, did the data analysis. If you read the paper, there's even some basic foreground cleaning to make sure you're not looking at the galaxy. And to me, what makes it impressive is that he was a PhD student. So this was his PhD thesis. And obviously, the CMB has come a long time since then. And here I'm just telling you, you've probably seen it, but it's usually shown in terms of these color-coded maps. So this obviously here is the galaxy in red, where you're not looking at the CMB. But up here, you're actually really looking at cosmic microwave background radiation, and particularly looking at the fluctuations. So the cosmic microwave background is relatively bright. Here you're looking at the fluctuations, which are much smaller. They're at the 10 to the minus 5 level, but you can see them in those maps in the temperature. This is the Stokes Q parameter, and similarly there's the Stokes U parameter maps. That's how they're usually shown. If you want to compare it with theory, it's more convenient to not use those maps directly, but to work with so-called multiple coefficients. If you have a function on the sphere, the natural reflex is to just decompose it in terms of spherical harmonics, and these are the expansion coefficients. For the Stokes parameter, that's not quite the right approach, because these are really components of a symmetric 2 tensor, so you want to expand them in terms of the eigensections of the corresponding Laplacian. These are the spin 2 spherical harmonics. You get some coefficients, and you can combine them. So these are not yet too nice because they don't have nice transformation properties under parity. But you can combine them in this way, and then this one transforms essentially like an electric field. This one transforms like a magnetic field, and so this is usually called AELM and ABLM, and we'll see more of those. Of course, the theory can't really predict a given realization. It can only predict ensemble averages. So what you're really measuring and comparing with the theory are the power spectra. So you square them and average them, and these are the angular power spectra that you've seen many times. So this is how you would compute them from a map. This is obviously a bit simplified because there's the galaxy along the way and so on, but that's the basic way you would compute them if you had full sky maps. And the early anisotropy measurements looked something like this. So this is a good snapshot from around 1997. This is around the first time we saw the acoustic. You can see the acoustic peak in the data. These are from Matt, Toko, Saskatoon are some of the early CMB experiments. Down here, the black points are Kobe. And it's around that time that people concluded that strings, monopoles, textures, whose predictions are shown here, are probably not what creates the perturbations in the cosmic microwave background. This is something that was still a popular idea at the time, that they're just created causally at the time. and it turns out that's not true. Now, fast forwarding to Planck, we have really nice angular power spectra of both temperature and also the polarization data. And here maybe just one comment is that this is not a fit to the data. This is using the prediction based on the cosmology that's extracted from the temperature data. So it's remarkable how well this actually fits. So it's a non-trivial prediction. So there was no fit to these data points. You just take these, measure the cosmology, predict what TE and EE should look like, and this is the agreement that you get. So in that sense, we think that we roughly really know what's going on. I want to briefly give you a little bit more of physical background as to what you're actually looking at when you're looking at these spectra. In particular, what you're looking at when you're looking at the power spectrum of temperature perturbations. And for that, let's look back at the plasma that's filling the early universe, and let's look at it not in real space like we did for the baryon acoustic oscillations, but let's look at it in a slightly different way, and let's think about it in Fourier space. So this plasma has some energy density. We can Fourier decompose it. There's some standing waves. The frequency with which they oscillate, because they're sound waves, they are proportional to the wave number. So if the longer wavelengths oscillate more slowly, the shorter ones oscillate more rapidly, and so on. This is the wave number, which is 1 over the wavelength. So shorter modes are on this side, longer modes are on this side. So if you look at the time evolution, we'll see that they oscillate more slowly here, more rapidly over here. And they oscillate until, again, the same decoupling happens and the photons decouple from the baryons, and then it's frozen in. And you're effectively looking at, when you're looking at the temperature power spectrum, you're really, to a good approximation, looking at the power spectrum of density perturbations in this baryon photon plasma at decoupling. So these ones oscillate, and then you get something that looks like this. This is obviously not really quite like the CMB spectrum I was showing you earlier, and it's not quite like the CMB power spectrum for good reason. First, there's baryons in the plasma, which introduce some inertia. So the baryons like to be in overdense regions, and so you get an offset in this, and that explains why the odd and even peaks are not the same height. So you get a lower second peak, second, fourth, and so on peak, then first and third peak. So the ratio between the first and the second peak is something you can use to measure the amount of baryons. You also see that this part isn't quite right, and the reason this part isn't quite right also has a good physical reason. The reason is that as you go to smaller and smaller scales, eventually you reach scales that are comparable to the mean free path of the photons, and you see diffusion, and this is what's happening here. So if you include what is known as silk damping, you get some exponential damping, and this is what the power spectra are. But you're really looking at the power spectrum of density perturbations in this baryon photon plasma, and so it's not too surprising once you know that you're measuring the power spectrum of density perturbations in the plasma that you can extract the composition of that plasma quite well. And in particular, you can measure how many baryons there are, as I said, from the ratio of even to odd peaks. The cold dark matter sets the depth of the gravitational potential, so you can measure how strong the perturbations are, the amplitude. This parameter here is the optical depth. This is what I briefly described in the beginning, arises from scattering of photons of the electrons after the stars reionize the universe. And then this one you can trade in for the Hubble rate, for example, and these ones are the ones that characterize the perturbations, the spectrum of perturbations. So you can measure those. We've also learned interesting qualitative things from, in particular, the measurement of the polarization. So I said that the temperature is measuring the energy density in the plasma. The polarization is measuring the velocity in the plasma. And this means that you can tell whether these perturbations at the time are forming or decaying. And it turns out, if you look if you work it out, that the negative sign here implies that the density perturbations that you're seeing on those scales are actually decaying. So they were there before already. So it implies that these perturbations are not forming at the time of recombination, but they existed at that time and they're decaying at that time when we're taking this snapshot. And together with general relativity, this means that they existed before the hot Big Bang. By hot Big Bang, I mean the moment when the universe was first filled with a hot and dense plasma. But this is something that we really know in a model-independent way from these, well, model-independent modulo, I'm assuming general relativity, but once you assume general relativity, we know these perturbations were already seeded when the universe first was filled with a hot and dense plasma. So what we've learned is this, that they existed before the hot Big Bang. We know that they're nearly scale invariant, very close to Gaussian, and as I said, they're adiabatic, which means that the overdensities in baryons are proportional to the overdensity in matter, to neutrinos. And the big question that many of us are interested in is what actually generated these perturbations. So that's the question we're trying to answer. And we don't have that many options in some sense as long as you stick to assuming general relativity. And to see that at least qualitatively, let's think about how we would describe this, this plasma. So we have the background equations for that we had was the Friedmann equation. And then we're looking at perturbations around that plasma because the initial overdensities, because the background is homogeneous, we can Fourier expand the density, the velocity field, and so on. And there's some characteristic scale, just for a given Fourier mode, is the wavelength. The other scale is the Hubble rate. Obviously, the modes that we observe today are inside our Hubble radius, so they're inside the horizon. We can actually see them. They're short enough for us to measure them. As you go back in time, it's interesting that this one here increases linearly with the scale factor, whereas the Hubble rate goes like 1 over t at all times. The scale factor goes like t to the 1/2 during radiation domination, so it drops like 1 over a squared here, 1 over a to the 3/2 here. And so as you go backwards in time, you see that the modes all become super Hubble as you go back. And this means that you can't really generate them causally unless in the early universe you have some phase where this picture changes again, and you have the perturbation or the momentum of your perturbation grow more rapidly than the Hubble rate. Or in terms of an equation, what you want is that the derivative of k over a over the magnitude of h is less than 0. There's two options here, as you can tell. There's one when h is just positive, then h is just a dot over a, as I said. And so you have d by dt of 1 over a dot is less than 0, which is the same as saying that a double dot has to be positive. So you have an accelerating expansion. H was positive, meaning expanding. A double dot is greater than 0, it's accelerating. And this is what we refer to as inflation. The other option is that you have a phase with h negative, and in this case you then get a double dot is less than 0, so you can have a decelerating contracting phase, but obviously we don't live in such a phase, so you have to somehow bounce and make it out into the expanding universe that we see. So this is the idea of the bounce. I've mostly been working on the inflationary idea, and the simplest system of inflation, if those equations don't mean much, I'll say it in words in a second, but the simplest system that you can write down is just the Einstein gravity coupled to a scalar field. So here the scalar field, essentially you can just think of a scalar field is something that is a single degree of freedom per space-time point, and the scalar field here I have in mind, or that you clearly need for such a phase, is you can think of as a clock. So there needs to be something that tells the universe when it should stop inflating. And that's what the scalar field is doing. So as it reaches some value, the universe stops inflating. And from thinking about it in this way, you also right away see that there should be perturbations. If you think about it quantum mechanically, you know that clock can't be arbitrarily precise. It has to fluctuate a little bit. So the universe stops inflating a little at slightly different times in different parts of space-time. That leads to the small perturbations. And the idea is that this is really the way the perturbations that we see in the cosmic microwave background are generated. So this is then the picture. Hubble, in this case, is nearly constant. So you generate the perturbations as quantum fluctuations when they're deep inside the horizon. They exit the horizon, and then obviously you might worry that they get modified through all the unknown physics that is going on. So we don't know how inflation, how reheating happens, how the energy density of inflation turns into energy density in the standard model particles, or the baryon photon plasma. We don't know how dark matter decoupling happens. There's many things in between, but it turns out you can show there's a conservation law, which is what we're using to actually make predictions. So they can compute that quantity during inflation, and that's the quantity that sets the initial conditions for the equations that describe the universe from a few keV, so after electrons and positrons annihilated, to the present. And so that's the basic idea. And it's relatively straightforward to compute them. Here are some of the quantities that I showed on the slide. So this just is the amplitude of the perturbations. And then it's usually parameterized as k over k star to the ns minus 1, just because this was just really a phenomenological parameterization. But you can compute these things. And it turns out they're given by, it's close to 1, which means the spectrum is close to scale invariant. And you can compute the departures from scale invariance, and the predictions agree with the observations. Otherwise, we wouldn't be looking at these models. Now, the question is, what can we actually learn about inflation beyond just the things we've already learned from the measurements of WMAP and Planck? And the interesting things, I think, that we still don't know, but that we have a chance of learning about in the next decade or so, is what's the energy scale of inflation. Obviously, it's a little bit embarrassing if you don't know the energy scale of a process, because that's one of the most basic things about a process. The other question is how far this field actually traveled. These are things that one can look for in the cosmic microwave background. There's also interesting questions that I don't have time to discuss, is whether there's additional light degrees of freedom. So there has to be this clock, but there could be other degrees of freedom. And these would show up in the 3-point correlation functions, which are tightly constrained already from the cosmic microwave background. The next way to make progress is with large-scale structure surveys. The other thing one could ask is, what is the propagation speed of the inflaton quanta? This might sound like a somewhat odd or strange question. The reason it's interesting is because it really tells you something about what was going on during inflation, in the sense that it's also how you would tell between different blocks of material. If I give you 2 blocks of material and I'm asking you to tell me what it is, and we paint them with the same color, let's say, so you can't just look at them to see what it is, you would maybe knock on them just to see what it sounds like, or more physically, what the speed of sound is in the medium. So this tells you about different inflation models. This is also something one can look for in the data, and we should get interesting constraints relatively soon. So I'll focus on the thing that we can learn from the cosmic microwave background. And as I said, one of the things we can learn from it is the energy scale of inflation. And the reason we can learn about the energy scale of inflation is that during this period, there's a prediction that just like the scalar field fluctuates, also the metric of space-time fluctuates and leaves an imprint of gravitational waves. That has an effect on the cosmic microwave background that one can look for. And the interesting thing is that the power spectrum of the gravitational waves is entirely set by the expansion rate of the universe. So if you measure that contribution, you're really directly measuring the expansion rate of the universe during this very early time. Or if you use Friedmann's equations, which told us that h squared is related to the energy density, it allows you to infer what the potential energy density in the scalar field is. And it's convenient to write it in this form. So right now, we don't really know what it is. R was the tensor to scalar ratio, so the ratio in power of gravitational waves to the power in scalar perturbations. And it's convenient to write it in this way for two reasons at least. So one of them is that r of 10 to the minus 2 is roughly what we might be sensitive to. And the other one is that r of 0.01 is an interesting theoretical limit, because that's the regime where the field moves a distance that's large or small compared to the Planck scale. And the interesting thing is that the scale that comes out is around 10 to the 16 GeV, which is so far looks like a coincidence, but maybe there's something to it, that this is close to the scale that we would associate with grand unified theories. You also see from the fact that there's this 1/4 power that a detection is very exciting, because you actually learn what the scale is. Upper limits, you have to think a little bit harder what you learn, because you're only really pushing the scale down by relatively little. So you have to push it down 4 orders of magnitude to get 1 order of magnitude in the scale. So pushing it down is relatively challenging. I'll briefly tell you a little bit about what the experimental constraints are. So here I'm just showing you the maps that you might have all seen around the time when the BICEP 2 discussion was going on. These are the maps that were observed by BICEP 2, and the exciting thing was that the E-mode signal was consistent with what you would expect from simulations. So simulations in the context of lambda CDM, so our standard cosmological model plus noise, whereas the B-mode signal that was observed was much brighter than the B-mode signal that you might expect in the absence of, well, the B-mode signal that you might expect if all you have is lambda CDM plus noise. The obvious question is it in the sky? I think everyone now agrees that it's in the sky. The second question is it really CMB you're looking at? And I think everyone agrees that it's not really CMB. So here you have a very nice map of dust, which is maybe not quite what you wanted, but it's still interesting, because with this map we can keep going, and actually once you have measurements at different frequencies, you can remove the dust, and that's the direction that everything is going. So these are really very, very deep maps, in the sense that if you compare them to the levels of Planck, so Planck has a sensitivity of a few microkelvin degree. This one you see is 87 nanokelvin. If you combine it with the more recent data, it's something like 50 nanokelvin. So they're significantly deeper. The way this happens is obviously that Planck spreads out its sensitivity over the full sky, and here it's just staring at a little patch. We were looking at this. Initially, I got excited because we've been working on stringy models of inflation that make a prediction for these kind of experiments. And so I wanted to understand what the data really means, and I started making the likelihood that was put out by BICEP just didn't include foregrounds at all. And so I wanted to make a foreground template, marginalize over it, and see how much of a primordial B-mode signal there actually was. And then the various foreground models that I got, they were all completely consistent with the data, so there was really no need to do a data analysis anymore. And there's also, this was really a measurement of some set of digitized maps that were floating around. That measurement was confirmed by Planck. And on the one hand, that was nice because it was reassuring to see that I didn't screw up the measurement. On the other hand, it was disappointing because it really means that what we're looking at here is just dust. The measurement by Planck really is a measurement at 353 gigahertz, where the dust is very bright and it's not measuring any CMB. What the maps allow you to do is really clean, or you can now use the Planck maps that you have of the dust to clean these BICEP maps and get tighter constraints on the tensor to scalar ratio than you had before. Here I'm showing you some of these constraints, the upper limits on the energy scale of inflation. And so this was what we had from Planck. These are the kind of contours that we get if we combine Planck with the BICEP data. And the improvement looks relatively incremental. I just want to briefly explain why that's the wrong way to think about it. So with the current data, R is constrained in two different ways. Planck and WMAP have been using that primordial gravitational waves contribute to the temperature perturbations on large angular scales, L about below 100 or so. At the same time, the main signature people are looking for now is the prediction or the contribution of tensor modes to B-mode polarization. And this is essentially, as well as you can do, is an upper limit of around R is less than 0.1. That's what you can get from the temperature measurements, and that's what we had from WMAP and Planck. This is what the current experiments are doing. These two likelihoods are essentially independent, and so you can look at the likelihood in this way, so you can multiply them, and usually, obviously, we're saying, okay, the tensors contribute the same to the temperature and the B-mode polarization, so we're looking at the diagonal part, but you can look at the quantity broken up and you get an idea where the constraint is coming from. Before the bicep measurement, the constraint was essentially entirely coming from the temperature measurement. So you had something like a tensor to scalar ratio less than 0.13 at 95% confidence level from the temperature data alone, and an upper limit on the tensor to scalar ratio from polarization alone of about 0.7. So there was not much information in the polarization data. Whereas once you add the BICEP2 data, you see that around the time BICEP2 released their results, the constraints on the tensor to scalar ratio from polarization and from temperature were comparable, but it was a huge improvement in the measurement of the B-mode polarization by about a factor of 7. And so that gives you an idea that this trend will actually continue fairly rapidly. This is just one more set of detectors included, already shifted it down. And there's a lot of experiments that are ongoing and planned to measure this signal. So this slide you've already essentially seen. These are the ones that are ongoing. One new experiment that will start construction relatively soon because Jim Simons decided to give $40 million to look for this signal and other things you can do with a cosmic microwave background is Simons Observatory. This is Brian Keating at UCSD is the director, and this will be an expansion of the existing site in the Atacama Desert and will be a merger of ACT and Polar Bear. And it's also a stepping stone on the way to an experiment that we've been actively trying to get an idea what it should be able to do, how much it would cost, and so on, that would be funded by the Department of Energy, which is CMB Stage 4, and I put something like 2020 to 2030 there, which would really be the entire CMB community coming together to make exquisite maps of the cosmic microwave background from the ground. So this would be a ground-based experiment, probably with two sites, one in the Atacama Desert, one at the South Pole. There's also the potential to get future space missions. Lightbird looks relatively promising, is a Japanese satellite with NASA contribution. Pixie is essentially another version or a more modern version of FIRAS that could measure the black body spectrum at much higher precision. The last time it was measured was really the FIRAS experiment in the late 80s and early 90s. And then another one that we're currently also studying is Inflation Probe, another satellite. It's unclear whether this one will happen for sure, I would say. I mean, it's mostly a study to see what one could do and whether it's worth it. So CMB Stage 4 really, just to give you an idea, is really the whole CMB community coming together. There was a series of workshops. We had a science book. If you're interested, you can take a look. The main science goals really, as I said, are to detect primordial gravitational waves or place an upper limit of something like 10 to the minus 3 at 95% confidence level. So this is significantly stronger than where we are now, about a factor of 70 stronger. The other interesting thing that I don't have time to talk about much, but it can do, is to measure the effective number of relativistic degrees of freedom with a precision of 3 times 10 to the minus 2. And it can also determine the sum of the neutrino masses at greater than 2 sigma, even for the minimum value of neutrino masses that's allowed for the normal mass hierarchy. So these are the main science goals. You can really do a lot more with the SE lensing. There's a lot of interesting things you can do with it. Roughly, the idea will be to survey as much of the sky as possible from the Atacama site and the South Pole. Roughly about 70% have 1 to 3 arc-minute resolution and a noise level of 1 to 3 micro-K arc-minutes. And this really you can use for a lot of things. I mean, you can place interesting constraints on light-dark matter, axions, cosmic strings, and so on. So there's really a lot of potential in these experiments. This is what the NSR plot I showed you before would look like. Notice that it's a logarithmic scale now. So if you have 10 to the minus 2 of R, you really get a high significance detection with something like CMB stage 4. You also get interesting upper limits. I don't have time to discuss them in detail, but this is kind of the upper limit here. This one is 2 times 10 to the minus 3 at 95% confidence level. And it really would disfavor, if it makes any sense to you, would disfavor all models of inflation that explain the spectral index we see with a super Planckian characteristic scale in the potential. So features that are larger than or equal to the Planck scale. For the neutrino masses, I'm just showing you the measurement here. So I'm not claiming that this can do what people do in neutrino physics experiments on the ground. It's complementary to it. It really, and that's why I'm putting it on different axes. I mean, it's really orthogonal what's being measured in cosmology and what's being measured in particle experiments, but I think that makes it interesting. So here I'm just as an example showing you the constraints on neutrinoless double beta decay. So this is one quantity which is very different from the quantity that's being measured in the CMB, which measures the sum of the neutrino masses. Even that statement isn't quite true. It's really weighted by the mean free path of these particles. So they're really quite complementary to the ground-based experiments, but would allow you to measure the sum of the neutrino masses, even if you have 3 neutrinos, even if for the minimal mass that's consistent with the oscillation experiments. Yeah. For ineffective, just for the people that are interested in it, here are the curves of what you can roughly do. So these are the 2 sigma predictions, the various things that you're seeing. So this is the contribution to delta ineffective, means the change away from 3.046. And if you have a single real scalar degree of freedom that couples or was coupled to the standard model early on, then decouple thermally at very early times, you get a contribution of 0.027. This is something we can't quite get to, but you can, in principle, detect single degrees of freedom, or fermionic degrees of freedom, or vector degrees of freedom. So this is really a way to do beyond the standard model physics, if you like. It has some interesting implications for many beyond the standard model physics models. I don't have time. I'm out of time. So let me just conclude by saying that lambda CDM together with the standard model explains all current data. For cosmology, the data I showed you was the supernova data, the baryon acoustic oscillation data, and the cosmic microwave background. There are some small tensions that I'm happy to discuss if anyone is interested, but really at the big picture level, everything seems consistent. And the CMB really provides a unique opportunity for us to study the early universe. And we're not anywhere near the end, so one can still do significantly better with the CMB experiments than we've done so far. You can study a number of interesting things with it. We don't currently have any evidence for primordial gravitational waves, but we're working hard to do a better job at measuring them. And as I said, there's many experiments that are already trying to do that. There will be lots of experiments coming online, and hopefully we can push the tensor to scalar ratio with those to about 10 to the minus 3. For other questions that I didn't have time to talk about, like bounds on non-Gaussianity, maybe even ineffective eventually, large-scale structure will be the next frontier. But in either case, so the next decade or two in cosmology should be quite eventful and exciting, and hopefully we'll learn a lot more about the early universe from all the experiments that are going on. So thanks.
Is there an easy way to see that the scale of inflation is related to the
that it's related to? To the gut scale. No, you plug in the numbers. It's also not obvious that it's necessarily too meaningful, because typically what I would think of from a field theory point of view when I talk about the gut scale, I think of maybe gut scale masses. This is not what's going on here. I mean, it's really the potential that's of order the gut scale, the potential energy density. If you imagine that it's m squared phi squared, which we know it's not, but let's just imagine that for a second. The phi is actually very large. I mean, the waves of the scalar field are very large, and it's just that the combination of this 15 m Planck phi in m squared phi squared would be 15 m Planck, so the 15 m Planck squared times, or 15 m Planck times the small mass eventually gives you the gut scale. So it's not obviously pointing you to mass scales in the of grand unified theories, but it's still interesting that that number comes out. I mean, the energy density in the not vacuum, but the energy density, the potential energy density would be around the gut scale in this case. We're working on it. We have another meeting on, well, I'm flying out on Sunday, so we have meetings every few weeks. So there was a group of people selected by the DOE and NSF to answer exactly this question. I don't think I want to quote numbers now and then they change and then people are unhappy. So we're working on numbers of how much that would cost. Typically, the numbers that are being thrown around are something like 150 to 200 million for the contribution by the Department of Energy. It's what we're working on, how much it would actually cost to build the kind of thing that one would want to do. Right now, we don't really fully know how much that is. I mean, it's off that ballpark, but the, order one numbers matter. How much progress has been made?
After this
so, I mean, I should say.
Future, right? Let's say you have CMB stage 4.
Yeah.
How do you get it out?
So the way you get it out is really by doing additional measurements in a way. I mean, the problem with BICEP was not that you couldn't have measured it at the time. That's just that there was only a measurement at a single frequency. If you have a measurement at a single frequency, there's no way to disentangle what's emitting. Everything contributes, so you have some contribution from the CMB, which was also there, not the primordial one, but the lensing contribution, for example, was also there. So there's a number of things that are emitting. There's typically the things one worries about is the cosmic microwave background that you want to measure. In the units, let's say we're working in units where that's constant across frequencies, so you measure it in TCMB. Then you have a contribution from the dust that rises as you go to higher frequencies, so it gets brighter and brighter as you go to higher frequencies. That's why you can use these higher frequency channels in principle to measure the dust. And then you can also use measurements of the low frequency information to measure the synchrotron, which gets brighter as you go to low frequencies. So the goal is certainly to have enough resolution in terms of frequencies to actually be able to measure the various components. It's not clear. Obviously, the modeling also has to be better. This is something that a number of people are thinking about. We've also been thinking about it with just MHD simulations and trying to put in some physical models of the dust to get a better understanding of really what the spectral dependence is. Right now, the best guesses or the best measurements we have are from Planck, which tells you that the dust, to a good approximation, emits like a gray body with some gray body. I mean, the beta is something like 1.59. The temperature is around 19.6 Kelvin. So there are, I think, really we'll have to measure it. And currently, the strawman configuration we have, for example, has 9 frequencies versus the single frequency that was there in the BICEP experiment. So the hope is that you'll measure it, but there's also certainly a lot of effort in modeling it. I don't know that the modeling, I don't think you can ever just model it and understand what's going on. I think you really need additional measurements to pin down both the dust and also at these levels, synchrotron matters. At these levels, it looks like even something like the polarized contribution of anomalous microwave emission might matter, so that's something we're including in the simulations. So when we're saying that these kind of things I can show you simulations. I mean, I have a lot of simulations, but.
Completely non-expert question.
Uh-huh.
People introduced this mysterious scalar field in the inflation model.
Uh-huh.
Presumably, it is not in the standard model, this scalar field.
Yeah.
Does the model or the approximate solution of the model tell you what happens to the scalar field?
Oh, what happens to the scalar field? It decays.
Remnant of it?
Most likely not. I mean, so typically the way it works in the typical models, what happens is there's some couplings of that field to standard model particles, maybe to standard model particles, maybe to some other sector that then decays into standard model particles, but there's some coupling of that field to other degrees of freedom. At the end of inflation, it decays into those particles, so there's nothing really left of it. In fact, even though we say it's light during inflation, it's not light on a particle accelerator scale. So the mass at the minimum of the potential for large field models is still something like 10 to the 13 GeV, so it's extremely heavy and short-lived. It doesn't really, it's not around today. Unless, I mean, there's ideas where maybe it's the Higgs, but it's not clear to me how.
The parameters of it are tested in your angular distribution of...
Yeah, you're not getting a very refined measurement of the potential, so it's not clear that we'll ever get a very refined statement about what the potential of that field looks like. That's why I think it's better to ask the kind of basic questions that we can answer, like what's the energy scale, how far did it move? So those questions we can maybe answer. The detailed shape is difficult to measure because you're really only getting two numbers, as you saw. I mean, you're getting the value of the scalar spectral index, and you're getting the amplitude that doesn't really allow you, and maybe the tensor to scalar ratio, so you might get some three numbers out of it, but that's not enough to really tell you what the potential should be. So I don't think we'll really be able to pin down.
But it has some predictions for the polarization of...
It does, I mean, but it's only really the energy scale that tells you what's going on there. In principle, there's additional predictions on just like you measure the spectral index of the scalar perturbations, you could imagine measuring a spectral index for the tensor perturbations, and that also is an interesting quantity to measure, but that's very difficult to measure, especially from the ground. So maybe that's something one can do from space. So that gives you one more number. In most models, that number is fixed to the scale. So it's NT is minus the tensor to scalar ratio over 8. And so we already know that it's essentially too small to measure with high significance. But so it looks like we're stuck with relatively few numbers, and we won't know the detailed shape of the potential. We'll just know qualitative properties.
Can I ask a related question? I mean, you mentioned that 2 ways out, there was inflation and bounce.
Yeah.
And you gave up on bounce. Is there a reason for that, or is it dead?
I'm not saying I'm giving up on bounces. I think it's interesting to explore both of them. For the bounce, I think currently it's a little bit difficult to control theoretically. So you want to have a solution that undergoes a bounce in a regime where general relativity is valid, which typically just doesn't happen. It bounces and all kinds of modes get excited. There are some ideas how you get around that and how you really control these bouncing models. I think for me, it's currently still more pleasant to have. So you might say, for the bounce, you might say, well, maybe someone figures out how to bounce and then it's all good. That's fine. But you need something new during that period. For inflation, once it starts, you don't need anything. It's just the basic kind of physics we're always using. For inflation, you might ask, is there anything special you need to get it started? And that, to me, is conceptually somehow a nicer situation to be in, but in principle, I think both are interesting, and there's people working on both ideas. Certainly more people working on the inflationary idea, I would say. But so I think if people... No, experimentally, it's probably easier to rule out, well, I think, yeah, I don't know. Yeah, it's difficult. So for the bounce, if you see a tensor signal, then you would likely conclude that it wasn't a bounce. The bounces, as far as they make predictions at all, I mean, the predictions they make is that you wouldn't see the primordial B-mode signal. So if you see a signal, you would conclude that it's inflation. That's one of the goals of the experiments. Ruling out inflation in the same way seems difficult because of the scaling, that the scale scales like r to the 1/4, so you just lower the energy scale of inflation a bit and you're below what you could detect. So.